Dear all, welcome to this chemistry lecture series. So in this lecture, I'm going to cover Unit 4. The topic is polymer chemistry and polymers, the macromolecular polymer chemistry. So this is part 2 of the lecture. Part 1, I have covered up to addition polymerization. In this part 2 lecture, I am going to cover the topics from condensation polymerization and conducting polymers. So with this, the module 2 will be completed. In between, I will also tell the important questions which can be asked in the class test as well as in the final semester examination. Okay, so before discussing about the condensation polymerization, I would like to uh, share with you that we are going to discuss about synthesis, properties, and uses of some of the important condensation polymers. For example, nylon 66, nylon 610, and nylon 6. Synthesis of nylon 66, 610, and nylon 6. Generally, you will find the synthesis methods given separately, but I tried to combine all three synthesis methods and I have presented here in a single slide so that it will be easy for you to compare one synthesis method to the other. Let's first discuss about the synthesis of nylon 66. So here we are taking a monomer with 6 carbon atoms. It is a carboxyl group containing dicarboxylic group containing monomer we are going to take. That is HOOC CH24 COOH. This compound is called adipic acid. Now count the number of carbon atoms in this molecule CH24, so 4 carbon atoms in 4 methyl group, and then you got one carboxyl group on the left and the other on the right. So 2 carbon atoms from both these carboxyl groups. So totally you got 6 carbon atoms present in adipic acid. Now let's take the second monomer which is given on the right, that is hexamethylene diamine, which means methylene groups that are 6 methylene groups are present. That's why we are calling it as hexamethylene. And also from the name itself, you can understand that it is a diamine. So 2 NH2 groups, one on the left and the other on the right are present. So now count the number of carbon present in this hexamethylene diamine. It is very straightforward. 6 methyl group, so 6 carbon. So both in adipic acid and hexamethylene diamine, you got 6 carbon each. So that's why whatever the condensation product polymer we form, that is nylon, we are naming it as 6. 6 represent the number of carbon atom in the monomers, that is in adipic acid and hexamethylene diamine. Now let's look at the reaction. So here condensation reaction polymerization means we already know that some simple molecules like water, HCl should be eliminated. So here from adipic acid, the hydroxyl group and the hydrogen from the amine group of the hexamethylene diamine react with each other to eliminate one water molecule. As a result, we know that carboxyl group and amine groups react with each other to form an amide bond. So we got this CONH bond and we are representing with N at the suffix. So which represent N number of this repeating units are present in this nylon polymer. Similarly, let's look at the nylon 610. From the name itself, you can say the monomer, one monomer will contain 6, the other monomer will contain 10 carbon atoms, and also this is a copolymer, so more than one monomer are used. So we are going to take subacyl chloride, subacosyl chloride. Uh, Here you got CH28 and then acyl group is present. Acyl group means RCOCl. So instead of here R is the methyl group and octa methylene groups are present. Here hexamethylene, here octamethylene groups are present and acyl groups are present at the left and on the right COCl group, and you are taking n number of subacosyl chloride and you are reacting with same hexamethylene diamine, that is 1,6-diaminohexene or hexamethylene diamine, both are same. So here 6 carbon atoms are present. Now here count the number of carbon atoms, 8 methyl groups, so 8 carbon. You got 2 acyl groups which have 1 carbon in each acyl group is present. So 8 plus 2, 10. So that's why we are calling it as 610. And now here the condensation reaction, I already told water or hydrochloric acid can be removed. So in this reaction hydrochloric acid is removed, that is chlorine atom from the acyl group and hydrogen from the amine group are condensed to eliminate one hydrochloric acid. It is a byproduct and you will get this amide product, the acyl product, right? Here also you are getting NH, so amide bond is formed. And let's now look at the third condensation polymer, nylon 6. So here you are going to take one as a cycloheptanol. Hepta, so hepta means 7 carbon. So that's why I number this. Cyclo means it's a ring structure. From the name itself, you can say. So aza group means we got the carbonyl and NH is present here. Heptan no, so keto group, double bond O. Aza group means NH is present here. Now let's number this one. So put a heptane 7-member ring and attach the double bond OC double bond O to the 7th carbon and put the NH group between the 5th and 7th carbon. Now do the numbering 1, 2, 3, 4, 5, 6, 7. So like that. You can also do the other way, like starting from um, uh, like one aza group. No? So you can start from here 1, 2, 3, 4, 5, 6, 7. So, 1 aza, 7 heptanol you can also do. The numbering you can also do the other way. So here in this particular compound, so the hydrolysis is happening. So here there are not two monomers, only a single monomer, and you are doing a hydrolysis process. And here one water molecule is added to this one. As a result, for example, if hydrogen is added to this NH mix, you will get NH3 plus. So exactly you will get the CH2 5, and here you are having C double bond O, and you are adding one more oxygen from during hydrolysis. So CH2 5 NH3 plus C double bond O single bond O minus. Now when you heat this solution, then polymerization process will happen and the cross linking will happen and condensation reaction will happen, which means this hydrogen and the other oxygen uh, will react together in the adjacent chain, and then it will eliminate one water molecule and you will get the proper amide bond at one end and the C double bond to this part here. So this is nylon 6. And now they will ask you to write this question nylon 6, how write the brief note on this synthesis of condensation polymer like nylon 6, 6, 610 and 6. Similarly, they may ask you to write two properties and uses. So let's see the properties of nylon 6 first. It has high molecular mass. Obviously, the monomers are high molecular mass, so the polymer will also be of high molecular mass and high tensile strength. This is a condensation polymer, covalent bond, so high tensile strength, does not soak in water. Similarly, the properties of nylon 610, good chemical resistant. It also resists environmental stress, resists salts such as zinc chloride. Nylon 6 is also a tough polymer with high mechanical strength, high elasticity and luster, and also it has good resistance to acids and alkalis. Let's see the uses of nylon 6. Mostly the nylon is used in making sheets and brushes, like polymer brushes, even the toothbrushes, paint brushes. The bristles are made of nylon 6. Surgical sutures. So after surgery, they will be doing sutures. Now, for that, that will be nylon. And also we use a lot of fishing nets are made of nylon, and also many other applications of nylon 6 are also there. It is also used for making pipe and hose components. The uses of nylon 610, mostly zip fastener. If you look at your the plastic or polymer zip fasteners, the track, zip fastener track, that is made of nylon 610. Electrical insulators, filaments for brushes, and also the uses of nylon 6 making textile and apparel. So it is also used in making textiles, and also engine parts and gears because it is has high mechanical strength and also surgical switches and dental floss. So you might have be using dental floss that are also made of nylon 6. So with this, let's move on to the other condensation polymer, that is polyethylene terephthalate. So you might be using the PET bottles, PET bottles. So that has a compound named as terephthalic acid. So this is also a condensation polymer, and it is also a copolymer. More than two monomer units are present. One is a dicarboxylic acid. Previous case for nylon we took adipic acid. Here we are, instead of methylene group, there we had hexamethylene, right? Um, Tetramethylene dicarboxylic acid, CH2 4 COOH COH. Here, instead of that methylene group, you are having a aromatic ring and carboxyl group at the both end, and you got the ethylene glycol. Ethylene glycol, ethylene, you know, CH2 double bond CH2. Instead of the unsaturated double bond, you will have a single bond, and each carbon will have one hydroxyl group attached. So it is a dihydroxy alcohol, ethylene glycol. Here, the hydroxy part of this ethylene glycol react with the hydrogen from the carboxyl group, and it will undergo condensation reaction, and it will form an oligomer. That is, the terminal end you will have C double bond O, single bond O, and then this cross linking will happen. So that is CH2 CH2. Exactly, you will have one oxygen. C double bond O will be present, and one more oxygen is here. That is what present here, and then CH2 CH2, and again this OH group will be cross-linked with the other one. Exactly, this is what it is written: COH. You got COO, aromatic ring, and then you got CO, and you got another O present here, and you have written here, and you got CH2 CH2 like that. And in the second step, you have to add the catalyst, and you have to heat the solution to 285 degrees Celsius, and solid phase polymerization you can carry out. In this case, you will get the polyethylene terephthalate, which is the polymerized product. Like here, you got N molecules from 2 to 4, like a short chain, but here it is a long chain, and it is highly robust and high mechanical strength, but they are not biodegradable. That is the important drawback with this polyethylene terephthalate when used in the PET bottles. Now more biodegradable polymers like lactic acids are also introduced, and researchers are trying to develop alternate biodegradable polymer for polyethylene terephthalate. This is one of the synthetic condensation polymers known to date. And then this reaction temperature is 80 to 300 degrees centigrade, and an acid catalyst like hydrochloric acid or other acid catalysts are used. And properties of PET, I have shown the picture here: PET bottles, and then cloths, and many other applications are this PET is used. High mechanical intensity strength, high resistance to acids and alkalis like other polymers, and low permeability to oxygen, carbon dioxide, and water. This also helps for the water to store in this PET bottle for long time without any carbon dioxide or oxygen contamination when they are closed airtight. And uses of PET, it is used in manufacturing shopping bags, water bottles containers, making bags, microwave containers, and carpets and packaging films. Now let's move on to the third condensation polymer. So in my lecture, I am covering only, I will cover four condensation polymer. So this is the third condensation polymer, synthesis of polyurethane. So here we are going to take the monomer diisocyanate, so which has two phenyl ring attached in between the there will be a methylene group, and also you have the isocyanate group on both ends. In the previous case, you have got one aromatic ring and COH on the left and right, that is terephthalic acid. Here you are having this aromatic ring attached with the isocyanate group. Exactly the same is present here, but these two rings are linked by the methylene group. This is how diisocyanate will look like. And then we are doing hydrolysis, and which means to the carbon double bond nitrogen, the water molecule will be added up. So you will get, this is how the structure will look like. You will have NHC double bond O, and OH you will get. You are having C double bond O, and then you are having OH you are having. Similarly, you will have this end. When you react this with ethylene glycol, then condensation. The first step only hydrolysis. Second step only condensation will happen, and ethylene glycol is a dihydroxy alcohol. So alcohol and this carboxyl terminator. So by doing hydrolysis, we are converting the isocyanate group into imine containing carboxyl group, right? NH is imine, and you got the carboxyl group, where this hydrogen from the this carboxyl terminal group will interact with the hydroxyl group from the ethylene glycol, and one water molecule will be removed. As a result, you got this NH double bond O, and a ether bond is formed, introduced or formed, and you got this ether chain. The backbone will be having ether as the functionality, and similarly the other end also this reaction will happen. So n type n number of polymers are formed, like 150, 200, like that. You can, depending on the number of monomer units, you can have the repeating chain in your polymer chain. So this is how the polyurethane is formed. Properties of polyurethane: so it has good abrasion resistant, good toughness, and low viscosity. And polyurethanes are used in flexible high resolution foam seating, like foam sealing, and the packaging material. They are used rigid foam insulation panels and microcellular foam seals and gaskets. Now, with this condensation polymer is over, now we are moving into the next important topic, that is natural polymer rubber. And also synthetic polymers, synthetic rubbers are also available, through which can be cross-linked by vulcanization. We will see all this natural and synthetic polymer. Natural rubber, here you can see that how the rubber latex is hanged here and how it is converted into rubber. It is a high molecular weight polymer, like 100,000 to 150,000 the molecular weight, and it is elastic. It can be stretched to 300%. Natural rubber, what is the building block of the natural rubber? Isoprene. Isoprene, it looks like this one: CH2 double bond C, CH3, CH double bond, CH2. The thing is, it contains two double bonds in its structure. It mostly occurs in the latex of various trees. So when you visit Kerala or other parts of the country, you will see they will make a slit in the trunk, and they will put some mostly the coconut shell. They will put it, and they will collect the rubber latex. Then they will collect all this rubber latex, and they will do the process, and they will convert it into natural rubber. So during the process of linking, head and tail linking happens in the isoprene molecule occurs, so that alternate single and double bond will be present. So this is the structure of natural rubber, cis isoprene. And properties of natural rubber: it is amorphous, it is very translucent, solid, not affected by any gases, strongly affected by the oxidants, acids and oxidizers, elastic in nature as well. And now this is one of the important topics. They will ask in 2 marks or a 4 mark question about the vulcanization of rubber. You should know what is meant by vulcanization. So basically, vulcanization is introducing sulfur to your rubber chains to introduce cross-linking between one rubber chain and the other chain. So what would be the effect of vulcanization? So once you introduce the cross-linking, then you are basically doing this with the help of sulfur. So you can tune this rubber content from 3 to 5%, and then based on the degree of cross-linking or the amount of sulfur introduced, the strength of the rubber can be varied easily. So here is the definition. It is a process that changes the synthetic and natural rubber into cross-linked polymer. So through the process of vulcanization, we can prepare cross-linked polymers. And look at here, the brown linear chain rubber chains are present here. You are adding sulfur, you are heating it up to 100 degree to 140 degree centigrade to introduce cross-linking, which means sulfur will cross-link between the rubber chains, and which is the cross-linking is indicated by the black thick lines in between the branched chains. So sulfur is the vulcanization agent for the natural rubber. Other chemicals can also be used. It is basically compounding rubber with sulfur at elevated temperature like 100 degree to 140 degree centigrade, during the process which sulfur enters into the double bonds of rubber and gets bonded and increases the toughness and stiffness of the product, that is vulcanized rubber. Uh, so the degree of vulcanization depends on the sulfur amount included or introduced. Flexible type rubber can be prepared by using 3 to 5%, whereas tougher variety of sulfur, that is ebonite, can be prepared by 32% sulfur. Synthetic rubber, there are two types. One is butadiene, that is Buna and Buna N and Buna S. We will see this, you already might have studied. Synthetic rubber, vulcanizable rubber like polymer, it can be stretched twice its length than the natural rubber. Properties, this high resilience, good mechanical properties, and also strongly affected by oxidation agent, that is a limitation. Uses, it is used in tire manufacturing. Most of the tires which we are using are vulcanized rubber, and it is also used in making shoe components, wires, cables, adhesives, etc. So the government controls the styrene rubber GRS. We will see. So you can see here in this picture that different parts can be like cables, and also the other parts can be cycle and automobile tubes, automobile parts, hoses, conveyor belts, and many more can be made out of this synthetic rubber. So let's take this butadiene. Butane, we know 4 carbon, diene 1 4. So this is one first and second carbon, you are having double bond. Third and fourth carbon, you are having double bond. So 1 4 butadiene. X number of butadiene molecules we are taking, and we are reacting that with styrene. I already told CH2 double bond, CH2 is ethylene. Instead of one hydrogen, you can replace it with the aromatic ring, benzene ring. Then you will have the styrene. So here, alternate single and double bond will be present. Look at here, CH2. This double bond you are having here, single bond will be present. Then this will be altered. So double bond will be present, CH. Here you are having double bond. So obviously single bond will be present. And this butadiene unit will be repeating. So instead of starting compound, you are having 1 4. But here you will be having 2 3. Diene molecule will be repeating in the linear fashion, and then this styrene unit will be attached through the, so styrene backbone will be same, and so you will have CH to CH. This is called SBR, or styrene butadiene rubber, where butadiene and styrene are cross-linked. And synthesis of Buna N rubber. So this is also other type, and Buna S rubber. Based on the monomer which we take, the rubber type and the properties and uses can also be tuned. So we will see, instead of 1,4-butadiene for the previous case, here we are taking 1,3-butadiene. So you will have the double bond between first and second carbon, as well as the third carbon you will have. For example, 1 2 3. So 3 and 4 you will have, 1 and 2 you will have 1,3-butadiene. And then you will react this with acrylonitrile. Again, the basic unit is ethylene, CH2 double bond CH2. Instead of one hydrogen, you are replacing it with CN. So that is acrylonitrile. Add the peroxide, heat it, copolymerization will happen, and you will get this product. That is, wherever, can you see that I have indicated with an arrow, which means the double bond is moving towards the cyanide group. Like here you have double bond, single bond, and it will, double bond will move here, and a new single bond will be formed with the CH2 terminal of the acrylonitrile, and wherever the double bond is present between CH2 and CH, that will move to the other one. Like that, this chain will propagate, and it will, you will have n number of molecules attached, units attached. So that will be, this is how a Buna N structure will look like. And then we will see Buna S, and then we will go to neoprene. Like similarly, we are taking same 1,3-butadiene, but instead of this cyanide group, you are having an aromatic ring, that is styrene. We already know, we have seen the polystyrene synthesis also, and PET also. Now, when we do this polymerization process again, the conjugate double bond will be converted to single bond. Can you see that CH2 single bond CH, and this will be moving to here. So second and third carbon you will have double bond, and this third and fourth carbon will have single bond. Obviously this will move to the next one and it will get attached with the CH group of the styrene, and the structure will be repeating like this. Now let's see the neoprene, where you have this butadiene, but this is 1,3-butadiene, exactly same structure. But the third carbon atom, you are having a chlorine atom. That means you are chlorinating the 1,3-butadiene to form chloroprene, and you will this compound, when you allow it to undergo polymerization, again the same story. The single bond will become double bond will become single, and wherever single bond you will have double bond, and this double bond you will have single bond like that, and n units will be n number of monomer units will be attached. This is called neoprene, chloroprene to neoprene. So basically you have to, when they ask about rubber natural and synthetic, you have to write about the natural rubber synthesis, and then these three synthetic rubber types you have to explain. Now I will move on to one of the important topics, conducting polymers. So we all know that polymers are not conducting, non-conducting by nature. Metals are conducting by nature. Why? Because the electrons are moving freely, or from one end to the other end, electrons can be conducted. That contributes to the electrical conductivity. But polymer generally they do not conduct electricity on its own. But there are certain polymers which can conduct electricity. Those polymers are called conducting polymers. This is one of the important questions from Unit 4 Polymer Chemistry. They will ask you to write about the conducting polymers. What is the conducting polymer? N doping or P doping in polymers. So either they will ask N doping or P doping. We will see what is N doping and P. To keep it simple, when the electrons are doped or responsible for conductance, that is called N doping. When holes are responsible, that is called P doping. Okay, so now let's see. Ordinary polymers obtained by usual methods are generally insulators. Whatever the polymers, addition, condensation polymers we discussed so far. However, there are some specific polymers which can conduct electricity. So what is the requirement for the conducting polymer to conduct electricity, or why do they undergo electrical conduction? The molecule should have a linear backbone. This is the first criteria. The second criteria is it should have extended conjugation. What do you mean by extended conjugation? Single double bond. So, I mean alternate double bond should be present in the structure. So whenever you have a linear backbone and when the double bond is alternating in its structure, then this double bond can hop. Now the electrons can, pi electrons can hop. That leads to the conduction. And also charge carriers, either positive holes, I told you holes or electrons should be introduced by appropriate dopant. The conducting properties of a conducting polymer can be enhanced by doping with suitable dopant. So let's see the origin of semiconductivity. So this is how a pi conjugated polymer looks like, and the alternate double bond in the backbone. So alternate single or pi bond allowed for delocalization of electrons through the overlap of p orbital. Now conducting polymer is over. Let's see the classification of conducting polymer. So the conduction due to extrinsic conjugation, we already seen backbone in the polymer chain. There are two major types. One is intrinsically conducting polymer. The other one is extrinsically conducting polymer. Intrinsically conducting polymer can be classified into two types: conjugated conducting polymers, doped conducting polymers. Doped conducting polymers means N and P dope. So these polymers all contain alternate double bond. This is formed due to the charge transfer agent or dopant. Either it can be a N-type or P-type dopant. And for the extrinsically conducting polymer means there is nothing like intrinsic impurity or dopant present. So extrinsically we have to dope something that can be, for example, you can take polymer matrix and you can mix it with conducting fiber like carbon fiber, as like that. Then you will form a matrix, mixed matrix, that will be contributing. That is called extrinsic conducting polymer. You are doing purposely, like blending polymers with other materials that are responsible for conductance. Even carbon particles you can blend, carbon fibers you can blend, and metal structures you can, metal nanostructures you can blend like that. Non-conducting, for example, polymers with conducting blends. So So non-conducting polymers can be blended with conducting polymer to make it conducting. Okay, let's take this well-known example, polyacetylene. So this is how a polyacetylene structure will look like: alternate single and double bond, and this you have this or the function group at the end. And if it is alternating like this, so this is opposite sides are having double bond, huh? So that is trans. Here the adjacent ones, horizontal ones are having, so this is cis form. So the polyacetylene can be simply prepared by using Ziegler-Natta catalyst. We already seen titanium compound, uh, organometal halide and transition metal halide with the composition for this one. And cis polyacetylene is a copper colored one with high conductivity 10 to the power minus 8 Siemens per meter. Trans polyacetylene is a silver colored with conductivity 10 to the power minus 3 Siemens per meter. Cis isomer can be converted to a thermodynamically favored or stable transform by heating at 1. So they are interchangeable. Cis can be converted to trans when you heat the cis form to 150 degree. So conductivity is generally increased when the trans polyacetylene is doped. When it is n-doped or p-doped, the conductivity can increase by an order of 2 or 4, 10 to the power 2 to 10 to the power Siemens per centimeter. So this is the first example of a synthetic conducting polymer. Acetylene we can take, and Ziegler-Natta catalyst you can put, and you can heat it, and polyacetylene will be formed. Like triple bond will be connected to double bond. So this double bond will be alternate, or alternate double bonds will be present. And by heating to 150 degree, cis form can be converted to trans form, which is highly thermodynamically stable. So applications of trans polyacetylene used as a lightweight electrodes for rechargeable battery, and it can be used in the manufacture of conducting films and powder, used in the manufacturing of corrosion resistant paints, and also used in storage devices. Since it is conducting, energy storage devices are also utilizing trans polyacetylene, micro actuators, compact capacitors, and even solar cells, LEDs, mobile television displays are also utilizing the trans polyacetylene. Now, this is one of the important topic in this polymer chemistry, in the examination point of view, p-doping. P-doping means holes will be, or holes means positive charge, will be doped in the polymer structure. So the polymers which have conjugation in their backbone, which means a double bond in their backbone, when they are treated with electron deficient species. We already know this concept. Electron deficient species means Lewis acid. Electron rich species means Lewis base. So you have to take a polymer which have a conjugation in the backbone, double bond in the backbone, treat it with the Lewis acid, electron deficient species. The best example is ferrous chloride, FeCl3, ferric chloride, or iodine vapor. Okay, FeCl3, ferric chloride, or iodine vapor you can take it, or iodine vapor and carbon tetrachloride. Any one you can take, and when you treat this polymer backbone with this Lewis acid, then oxidation will happen and it will introduce a positive charge in the molecule. So you're taking polymer, Lewis acid, FeCl3, ferric chloride, and then p-dope polymer or oxidized polymer form will be formed, which means positive charge will be introduced. Let's see polyacetylene. You just put CHX, 2FeCl3, CHX plus FeCl4, and adduct will be formed, and FeCl2 will be removed because we are taking 2FeCl3. Similarly, you can take 3I2 or iodine CCl4, and you can form 2CHX plus and I3 minus. So during all this process, one electron is removed from the pi backbone of the conjugated polymer to form a radical cation. So radical cation means you will have a dot and a plus charge polaron. So which again loses another electron and forms a bipolaron. The delocalization of this positive charges contributes to electrical conduction. Let's see the polyacetylene backbone. Alternating single and double bond is present here, and you have the electrons here, conduction band, valence band, HOMO and LUMO is present here. The polyacetylene is generally a neutral molecule with extended conjugation, double bond and single bond. Its conductivity is generally low, but when you dope with suitable dopant, conductivity increases. As I told, Lewis acid you have to take either ferric chloride or iodine carbon tetrachloride. So once you react with this one, then you are having this double two electron. You are removing one electron, so you are forming a positive charge. Similarly, the adjacent double bond also have two electrons. So if you remove one, then you will get a one positive charge. So like that, this positive charge will be moving to the left and this positive charge will be moving to the right. So that's how the conduction happens. So now N doping. So when Lewis bases, previous case we have we I said that you have to take a conjugated polymer. Now with the Lewis acid you have to react. For N doping it should be electron rich one. So you have to treat with the Lewis base electron rich species with the polymer having conjugation. And here there oxidation will happen, here reduction will happen, which means the polymer will accept the electron. When the polymer accepts the electron, it will get the negative charge. That's it. Polymer plus Lewis base and it will form electron dope or electron rich polymer, that is N dope polymer. So let's take polyacetylene again, CHX plus you are taking sodium naphthalite, so you are having negative electron. So we put it is a sodium salt. So Na plus and minus is here. So this Na plus will combine with this one and then it will add one electron. Na plus CH X minus the salt will be formed. N-doped polyethylene will be formed. So basically we are introducing electron. And here you will get the neutral molecule naphthalene again. So this is how the N-doping happens. You are voluntarily introducing electrons into this one by treating with the electron-rich species, and the polymer undergoes reduction during this process and accepts the electron, and negative charge develops in the polymer backbone. As a result, the negative charge will be hopping that leads to the conduction in the polymer chain. So, extrinsically conducting polymers are called as ECPs, which are over their conductivity due to the presence of externally added in the ingredients. They are called extrinsically conducting polymers. There are of two types: conducting elements filled with polymers (CEFP), filled with conducting element, and blended conducting polymers (CFP) and then BCP. Let's see one example, poly 3-hexyl thiophene for the extrinsically conducting polymer P3H2. Here we are taking 3-hexyl thiophene. So which means a hexyl group will be present at the third position, 1, 2, and 3. Hexyl group is present. C6H13 hexyl 1. We are taking this one. And Lewis acid you are taking FeCl3, perchlorate, N moles, and then oxidative coupling will happen. Nitrogen gas and chloroform you are taking CHCl3, and as a result the polymerization will happen and you get poly 3-hexyl thiophene, so I put N and 1 ferrichloride will be this is the adduct. N moles of ferrichloride will be, if you are taking ferrichloride, N moles of ferrous chloride FeCl2 will be formed as an adduct. So this is how the thiophene the compound will looks like. You will have a sulfur heteroatom, heterocyclic compound. So basically 5-member ring, 1, 2, 3, 4. In the 5-member ring, you will have this sulfur atom. Properties: P3H3 is a derivative of polyethylene semi-crystalline polymer. The Tg glass transition temperature of the P3H3 is 12 degree, and also high tensile modulus. It has high tensile modulus around 200 megapascal or 1 gigapascal. It is used in the optoelectronic and electronic fields, mainly in energy storage devices like solar cell. Polyaniline is a well-known conducting polymer which is widely used in energy storage devices like supercapacitors, batteries. It is a very good electrode material, good conducting properties. So all you need to do is take aniline. So aniline is the benzene ring attached with the NH2 group, amino group with a electron-rich nitrogen, that is a lone pair of electron. So when you add the hydrochloric acid, so it will act as a oxidizer and also an oxidant and the catalyst. So it will provide the protons. So this proton will abstract the lone pair of electron from the nitrogen, and then the electron transfer will happen, and then this chloride ion will abstract the electron from the sigma bond as well. As a result, since it is donating the electron, here protonation is happening, so NH3 plus will form and a proton positive charge will form because it is donating the electron, and then the chloride ion will be having completing its octet electronic configuration, and since it abstracted 2 electrons, it is having negative charge. So this is called anilinium chloride. So this is easy to synthesize, low cost and high environmental stability. And polyaniline can be synthesized by this type of polymerization is called oxidative polymerization. Why? Because you are using an oxidant or an acid as a catalyst. Stirring at 0 degrees centigrade. After adding the acid, this will form anilinium chloride, and you stir the reaction mixture in an ice bath at 0 degrees centigrade. And you have, since it is oxidative polymerization, this is only a catalyst, right? So you have to add an oxidant as well, that is ammonium persulfate, NH4 to H2O, which is a very good oxidant, strong oxidant. And then this will oxidize, and it will form the quinonoid and both benzenoid structure in the structure. So N double bond, N will be repeating. So benzenoid means NH, quinonoid means N double bond N. So this structure will be repeating, and as a result, the electron delocalization can happen, and it can be highly conductive. Similarly, the polyaniline conductivity can be tuned by doping with certain inorganic ions as well. So the uses properties I already told: easy to synthesize, low cost, high electrical conductivity, high environmental stability, and also it is an anti-corrosive material used in LED, smart window, supercapacitor. And ECPs, this is the last one. So the extrinsically conducting polymers. When carbon black or other metal oxide, they are naturally conducting. Carbon black is also conducting, carbon nanotube, carbon fiber, these are all conducting. When you combine with metal oxides or metal fibers are added, and when you mix together, the polymer becomes conductive. So these are act like an additive. So the minimum concentration of the conducting filler should be optimized, and it is the concentration that is required to start the condensation, that is called percolation threshold. So the filler or the ingredient that percolate have more surface area, more porosity, and filamentous nature. Due to these reasons, they can enhance the conducting properties. Important characteristics of ECPs include: they possess good bulk conductivity, they are cheaper, they are light in weight, they are mechanically durable and strong. They are also easily processable in different forms, shapes, and sizes, depending on the application. So blended conducting polymers, BCPs. So these are the type of polymers obtained by blending a conventional polymer with a conducting polymer. Again, physically or chemically, this blend of polymers will conduct the electricity. Such polymers can be easily processed and possess better physical, chemical, and mechanical properties. So with this slide, I would like to complete this module, polymer chemistry, macromolecule chemistry, and this is unit 4 in BTech Chemistry syllabus. And this is the part 2 of the lecture series. You can also watch part 1, which cover the up to topics up to addition polymerization. In this lecture, specifically, I have covered the topics conducting polymers, particularly the condensation polymers is the first part of the second lecture 2 series. Okay, in part 2, the first part will be mostly about the condensation polymers, their types, and how we can synthesize properties, etc. Then we move on to the condensation polymers, their types, and also their properties and uses. Particularly, I want to emphasize N-type and B-type dopamine are the important questions from this topic. So you have to read and practice, take polyacetylene, and you can explain this concept as we discussed in the previous slide. And thank you for watching. So with this, module 4 is completed. Thank you.